Hello. Hello. Can you hear me? Yeah. So today we will continue with the instructions of the language of the computer. There are some comments in the chat mentioning that sometimes there are genuine questions. So yesterday I was also using the top, but I didn't see anything. If you want that we move, instead of having it anonymous, having it so registering into the chat instead, in order to avoid people to just make a lot of fun. So just let me know, and I will make that it's compulsory to register to the chat in order to write. Otherwise, I will still try to see the real answers. If you see that you have a question and a genuine question, and I go to the chat and I don't see it, you can just also ask me with voice. Okay. So yesterday we saw how the instructions of my program are converted to what we call matching language or matching code or matching code. So I have an instruction in C, and then we saw that the equivalent instruction in assembly language. So today we are going to be how this assembly language actually translates into bits, into ones and zeros. So first of all, we are going to see how to represent some of the instructions we saw yesterday, but in the matching language. So the instructions we saw yesterday are encoded in binary bits, so in zeros and one. This is what we call matching code, and we have seen that the instructions in the instruction set we are using has a length of 32 bits, which is what we call a word. Remember that registers were double words, were 64 bits. And we are going to see how actually each of these instructions is encoded in these 32 bits. So again, this is one of the design principles we started watching yesterday, making it simple and regular in order to make it cheaper and increase the performance. So the first type of instruction is what we call R format instruction. The R stands for register. So all these instructions, this format is for all the instructions which operates on registers. For instance, the addition we saw yesterday. So what we have here is that the operation code, the add, the sub, or the operation we are doing is encoded using 11 bits. Then remember that in the case of the add we have 2 inputs and 1 output. So in this case the output is RD, register destination. So here it will be stored. In this case we are having as an example the addition. So RD will have the value of the addition. Then we have 2 operands, 2 inputs. Remember, we are summing element 1 with element 2. So element 1 will be in register N. N doesn't mean anything. It's just the author decided that argument 1 was N and argument 2 was M. So in the addition, the operand 1 will be in register N, and the operand 2 will be in register M. And then here there is a field which is called shift amount, and for now it will be just 0. Okay? So we are going to see an example of this later. So today there are 4 slides that I would like that you listen to me. So now the next 3 slides are very important, so please listen now to me. So here we have again the same format as before, but with colors. So remember the instructions we saw yesterday and the thing I have commented just now. So the operation code is something, a value that is agreed in which I encode any operation. In this case, for instance, the operation will be the add. Then register destination, which is the register where I'm going to store the sum, is here. And then we have the other two inputs, which are here and which are here. The shift amount is not used in this case. So now we go one level below. So instead of using the RD, RN, RM, we are going to use real registers. So we mentioned yesterday that we have different registers. So here, for instance, we are using register 9, 20, and 21. So this instruction will do the operation we have here. Register 9 equal register 20 plus register 21. So till now, it's more or less what we already know from yesterday. So now, how we do convert this to zeros and one? So in this case, there is a convention which says that the operation code for the addition is this number. When I say 10, I mean in decimal, okay? So here we have that this the operation code for the add operation is this code. Then what we have? Register destination, which is in this case 9. So we just put here number 9. And we do the same with the other registers. Register N, which is register 20, which is here. So here, register 20, the shift amount, we have mentioned that for now it's 0. So we just put here the 0. And then in blue, we have the second operand of the addition, which is register 21, and we put it here. Okay? So this is in just decimal, just to make it clear to you. But now, what we are going to do is actually convert this to binary. This is what actually is stored in the machine. The other types of so using decimal, hexadecimal is just for humans, for making it easy for us. But what the machine uses is the final in binary. So in the end, this instruction here, add register 9, register 20, register 21, will be stored in the machine like this. So we have here the operation code, which is just this decimal value converted to this. We have the destination register, which is number 9, which is those 5 bits, which are just number 9 in binary, and so on. We have all the registers. Is this clear? Yes? So now, the only question is, how do I know the operation code? Because now I have just told you that the operation code for the add, it was this number, but if instead of an add operation, I'm going to use a subtract operation, what I need to do? So we will see it in the next slide, but just to make sure that you are understanding what we are doing here. So we have this code in high-level language. Register temporal register 9 is equal to G plus H. What we saw yesterday is that this translates into something called assembly language, which was add register 9, register 20, register 21. And what we have seen now is that this translates into actual machine code, and this is what the machine is using. So now, let's go back to how calculate the operation code. So remember that yesterday we saw this reference data. It was a PDF that we have. Remember? In which we have all the operations, all the formats, and so on. So what we are actually doing now is going to this reference data, and we see, okay, where is the add instruction? So it's here, in orange, highlighted in orange. So here we have the add instruction. And then we say, the operation code for this instruction is this number here. Sorry, it cannot be read. So 458 in hexadecimal. So what we do now is we just convert this number into binary. We can also convert it into decimal if we are not going to actually use machine code, but it just depends on the number we want to use. And with this, we have the operation code. So now you have everything to encode any operation. So you know how to encode all these registers here, and now if the operation changes, for instead of an add, I have a sub or whatever, you just need to go to the reference data and you look for the value for the opcode, and that's all. Everything we have say here, it's in the reference data. So here we have mentioned the add operation. We have mentioned the format of the add operation is R format. So if we go into this reference data, we see R format. So, sorry. So R format, okay, the operation code is stored between bits 31 and 21. Then we have register M that we have mentioned is output 2. How do I know that this is output 2 and not, input 2 are not input and not input 1? So if you go again to the add, you see that here you have that register RD is equal to register RN. So Rn is the first operand, and register Rm. So Rm is the second operand. So it's the same for every other operation. If you continue with the format, you have here, so here we have the operation code from bit 31 to bit 21. Register M, the second input register, is from bit 20 to bit 16. Then we have the shift amount, then we have register N, and then we have register destination. So for any other operation, is the same. For any other instruction, is the same. We just go here, we see the instruction, we see the format, we have all the format in the reference sheet, we have here the code, and we have here how what is the operation doing. So any question? I didn't see any question here. Anyone has any question? No? Everything clear? So this is the base for everything. If you know how to do this, then for any other instruction is the same. So now what we are going to do is just commenting other formats, but you will see that more or less is the same. So the format instructions. D here stands for data transfer instructions. This means that we are transferring data, usually for load and store instructions. So here the same. We have 11 bits for the operation code. Then we have 9 bits for the address of the memory. We remember that yesterday we commented that basically in an assembly program what we do is transfer data from memory to a register, do operations in the register, and then moving the data back to the memory. So here, what we are indicating is the address of the memory. Then we have op2, which just expands the operation code if needed. And then again, we have two registers. In this case, we have register N, which again is the, as before, is the register, the input one. And then in this case, instead of register destination, we have T from target, register target. The change in the name is because this format is for load instructions, so we are storing data from memory in a register, and also for store instructions, we are storing a data from a register to memory. So that's why here we have a target register. So sometimes this will be the destination, and sometimes it will be the source. Again, here we are commenting one of the designs, the principal designs we started commenting yesterday, that says that good design demands good compromises. So in this case, having different formats make it a bit more complicated, but as soon as all of them has 32 bits, it's easy for us, for keeping the instructions uniformly. So an example with this format, again with colors. So the operation code, in this case, is load and scan register. So we have the register target, which means the register in which I'm going to transfer from memory to the register. And then we have the Rn, which is the first input, which in this case is the base address of the array in memory. So here what we have is, for instance, that we are going to load in register 9 the address in register 22 plus 64. Remember that we were using 64 because this operation uses an scale offset, so 64 was the index 8 of my array, of the array. Okay, of the array in this case, which is which base address is in register 22. So, assuming all that you know from now, will you be able to convert this to matching code? What do you think? You have the reference data in Canvas, so will you be able to do the same that we have done for the I format for this example? I give you some time. The reference data is on Canvas. You have also the slides in order to follow the previous one. This is so here up 2 will be 0. Yeah, 0, and then this is, yeah, I think so. So it seems well, yeah. Okay, you have it? Any problem for doing this? No? So we have just done the same as before for the other instruction. We have just gone to the reference data. We have seen that the operation code for this instruction is this number, and then for the rest we have here the address for this field is 0 from now. Then the register N is 22 here, and register 9, okay, is the same as before. So we have this in decimal, and then we have just converted this to binary. So it's the same as before, but we just have a different operation code, a different field here. The address is a new field, but it's more or less the same. Okay? So now, the third type of format instruction that we are going to see today. So it's the I format. In this case, is for immediate. The I is from immediate. Remember that apart from the addition, we have the addition immediate, which instead of adding 2 registers, we were adding 1 register and 1 immediate value or 1 constant. So in this case, we have the same as before. We have operation code, but notice that here, instead of using 11 bits for the operation code, we are using 10 bits for the operation code. Then we have the immediate value. In this case, this is, remember yesterday we were adding register 9 plus number 4. So here we put the immediate value, the 4, the 5, or whatever we are adding. And again, here we only have one register as input argument, because the second input argument is an immediate value. So we have register N, and then again register destination. So let's do an example again. So now here we have a new thing. As I have mentioned, here we have only 10 bits, but before we had 11. So the problem here is, in order to reach this number, if you go to the reference data, you go to the @intermediate, which is the immediate, sorry, which is the one we are using, and we see that here we don't have just one number, we have 2. So which number should we add here? So what happens is the following. As if we are using only 10 bits for one instruction, but for other instructions formats we are using 11, then if we want to know if one operation code, if we want to identify by 10 bits that there is no operation code which could overlap with another operation code with 11 bits, so we need to avoid anyone using those 2 hexadecimal numbers, because otherwise I will not be able to say by the operation code if this is an operation code for an I format instruction or for another instruction using 11 bits. It's clear? So I'm blocking those 2 hexadecimal operation codes for only one operation, the @immediate. Why? Because I'm only using 10 bits and I don't want to be I want to be able, with only those 10 bits, I want to be able to say that this is an add immediate and not other instruction. So any other instruction with an operation code with 11 bits will not have those initial 10 bits. It's clear? Yes? So the actual operation code will be only the 10 bits, the ones which are common in the two hexadecimal, well, in the two values that I'm reserving for this operation code. So in the reference data, when you see that you have two values, it's always the same. Those two values will translate into 11 bits, and you will have 11 bits for one value, 11 bits for the other value, and you just need to, and the operation code will be the 10 most significant 11 bits, so the ones which are repeated. Clear? So, good news. Apart from calculating the operation code, as I have mentioned, you can also go to the second page of the reference data, and you have the operation code in binary. So the one for instance, we have seen now the one for the add. You can see it here. And the one for the add immediate, which is just 11 bits. And this is what we have explained, that for the operation code of the add using 11 bits, we are using only one hexadecimal value, and for the add immediate, we are using 2 because we only use 10 bits. Clear? Yes, we have labs tomorrow, 9 a.m. You don't need to learn the reference data. You will have everything you need. You only need to know how to use. So if I give you the reference data, you need how to use it to encode the instructions. So tomorrow's practical will be regarding assembly language. So you will have instructions, you will have bits, and you will have to encode or decode instructions. Yes, the test will be similar to the one we did in the for the first chapter. Will be multiple choice. Okay. So now, how everything is stored in memory. We know how we convert the instructions to assembly language and then to binary. How is this actually stored in memory? So we have it in binary, we have bits. We just store it as any other data. Remember that we already know how bits are stored in memory. So here, what we have in memory, it could be the instructions that we are commenting now, and we could have a matching code like the one we are seeing now for a program. For instance, here I will have the PowerPoint program matching code, which is running, and then I will have also my presentation, which is another data. Here you have the sample with an accounting program and the payroll. You could have also a book test, and in this case I have the reference data. and you could have also an editor for programming, assembly language or whatever. So the important point here is this bullet here. So how we can run the same program in different computers. So this instruction set that we are seeing is standard. So is remember that we told that it was the interface between the software and the hardware. So as soon as you are following the instruction set, then what happens below is the machine who needs to manage it. So if the machine supports this instruction set, it will run your program. So that's how we allow the same program run in different computers, because this instruction set is standard and is followed by hardware manufacturers. So now we know how to represent instructions in the computer. Now we are going to see logical operations. You have already seen with Charles and, or, and not. So the new thing today is just shift left and shift right. You have here the equivalent operations in our instruction set. So one of the new operations is shift left. So imagine that we have this number. If we shift left by 1, which means that we move this one position to the left and fill with zeros, what we are actually doing is multiplying by 2. So this operation, shift left, is equivalent to a multiplication. So if I shift left by 2 instead of by 1, I'm multiplying by 4. And if I do the same by 3, then I'm multiplying by 8. Simple? Clear? When we move right, what will happen? So if we move left and we multiply, if we move right, so probably we are going to divide. So the same. If I shift right, so this one here, we move it one position to the right and fill with zeros. What we are doing is dividing by 2. If we shift right by 2 positions, we divide by 4. So the original number, which was 8, divided by 4, we have that it's 2. And again, if we shift right by 3, what we are doing is dividing by 8 the original number, so we have 1. Clear? So this is just a summary of shift left and shift right. You have here in red the numbers of positions you shift. If you do 2 power to the number of positions you shift, then you have the number by you are multiplying or dividing. So coming back to the instruction in our instruction set. So this is called left shift logical, and for the right we have left right logical, which is LRL. The format is the same. So here we have again the same. We have an operation code that is in the reference data, and we have register destination, register input 1, register input 2, and shift amount. So in this case, we are using this field, the shift amount field. So in this case, we are shifting left by 4 positions. So this is where we use the shift amount field. And this is what I have already mentioned. When we shift left by I bits, we multiply by 2 power I, and right is the opposite. You have already seen the AND, OR, and NOT with chars in with 3. Here, the only thing that happens is that for the exclusive OR, instead of calling it XOR, the authors of this instruction set decide to call this EOR, exclusive OR, but the operation is the same. And for the OR, in the instruction for the OR, instead of having only one R, it has two R's. So this is one sample of an instruction. You already have seen this with chars, but it basically is used in order, for instance, to mask some bits in a word. Then we have the OR instruction, which is the opposite, in which we could use this to include some bits. And the exclusive OR, that remember I told you it's EOR, not XOR, is also good for differentiating operations. So the only new thing that we have seen here is the shift operation. You already know the other operations, and what we have mentioned here is how those operations are encoded in this instruction set. So conditional operations. This is the last part of today's lecture. So basically what we are doing here is deciding if we follow with the next instruction or if we jump to another instruction. We have different ways of doing this. For instance, we have a CB set which says that I think that it means compare and branch is 0, which means if the register is this register is equal to 0, then we go to this address. We use labels in order instead of using addresses because it's easy for us, for the programmer. So at some place in my program, I will have a label, we will see it later, which will be L1, and we will go there if this condition happens. The contrary will be compare and branch if not equal 0. So if the register is not equal 0, then we go to this label, which is basically an address in my program which runs a different instruction than the following one in the code. And then we have a condition, a branch with any condition. So if you have the B for on branch, you just go to this label. If you see here, I have mentioned the formats. So CB format, compare and branch format, and branch format. If you go to the reference data, now you know how to interpret this. So we have here CB format. We know that the operation code is from bit 31 to bit 24. And then the rest is for the address of the condition, and here is the target register. In the case of the B format of the branch, we have something similar, but we don't need a condition. We just have a branch address. And again, you know how to look for the operation code and everything. So let's see an example here. So for instance, we have an instruction at the beginning which is just making register 22 equal to 10. Remember that this register X set R is register 0. So then we have a label here. Remember this L1 we have mentioned before? Remember we have said that L1 was a label in my program. So in this case, loop is one label of my program and exit is one label of my program. These labels are translated into addresses, but it's better for humans to put a label instead of an address here. So then what we do here is, okay, we have register 22, what we have previously initialized to 10, and then we are subtract 1 from register 22. So in the first iteration, if register 22 was 10, now it's 9. So then we move to the compare and branch if 0. So then register 22 is equal to 0. So 10 minus 1 is 9. So no, it's not equal to 0. So then I don't take the branch because this is not true. So I go to the following instruction, which is go to loop. And then I do this again and again. And after 10 iterations, this condition here will be true. And instead of doing the following instruction, I will go to this label, which is exit, and which actually finish my program. So basically, I'm doing a loop 10 times, and in the iteration 10, I just jump this instruction, and then I finish. It's clear? Any question? Wow. So I have already mentioned that tomorrow we will be doing things similar than today. So we have seen how instructions are represented. We have seen logical operations, and tomorrow we will see procedure calls. So thank you very much, and have a nice evening.